On to our fourth talk, efficient privacy-preserving recommendations based on social graphs. And it is going to be presented by Aidmar from TU Darmstadt.
Okay, hello everyone. So I'm Aidmar Wainakh from Technical University of Darmstadt. So, as we all know, there are many services in online social networks which depend on recommendations and recommender systems. So we recommend new friends, we recommend new articles in the social networks, and there are many techniques are used to generate these recommendations. In this research, I'm focusing on association rules mining technique. So just to remind you, the association rules technique captures the relations between different items, and the items could be any topics, interests, groups, whatever in the social networks. And building these rules between the items, we can recommend you. So we can see here, for example, if you are interested in politics, in technology, so we recommend you the politics groups, for example. To build these rules, actually, we have the first phase, which is building what we call frequent item sets, which are the items which are observed in the datasets frequently together. So based on the frequent item sets, we build the association rules, and we have the different parameters as the support and the confidence which we use during the process. However, dealing with the user data actually raises several privacy concerns, especially when this data contains some sensitive personal information about health, about political view, or homosexual or sexual orientation, for example. And actually, in the context of social networks, there are several solutions or proposals to solve the privacy concern. So, for example, we have the decentralized social networks, which focus on building peer-to-peer networks to let the users control their own data. So we eliminate the role of the service provider, which controls usually all the data, and we build peer-to-peer network between the users. Another example for solution is the hybrid social networks, which is a combination between the decentralized and the centralized social networks. Without going too much into the details of this proposal, the main idea of these two solutions is to give the users the control of their own data. So we will be dealing with distributed data. Each user controls his own data. And now if we want to build the association rules, we have to deal with distributed data in privacy-preserving manner. So in the research domain of distributed privacy-preserving association rules, the main requirement, we have multiple parties. Each party has a data, let's say hospitals. Each hospital has the data of his patients, and these hospitals would like to collaborate and build association rules based on their data without disclosing their own data to each other. So this is the main requirement here. So the leading actually approaches in this domain of research, mainly based on cryptography primitives, like the cumulative encryption, like the several protocols and secure multi-part computation, and elliptic curves encryption. And unfortunately, all these approaches actually cause very high computational and communicational costs, which make actually applying these approaches in large scale application is not possible. And therefore, in this research, we were focusing on improving the efficiency of these approaches. And instead of focusing on the encryption or the cryptography part, we're focusing on improving the efficiency of the association rules mining. And one approach to improve the efficiency is data sampling. And as we are dealing with distributed data in my setting, so data sampling is equivalent to user sampling actually. So usually in sampling, we are trying to replicate the distribution of the characteristics we find in a population in the sample. However, in the association rules, a good sample is a sample containing the frequent item sets. So this is what we mostly care about, because all the items which are not frequent enough, they will be discarded during the association rules mining anyway. So the question will be how we will detect the users who have the frequent item sets, who have items are commonly shared between the users. And to answer this question, we have to consider 2 points. So the first one is the theory of homophily, which says that the users who are similar tend to be connected in the social graph. And the second concept is the influencers. So more than 50% of Twitter users, for example, they rely on recommendations come from friends and influencers in their networks. And based on these 2 points, we propose that having a good sample requires to have influencers included in this sample. And this sample in this way will represent a large number of users. And to obtain such a sample, we propose to use a random walk, which has come from the graph theory. Why? Because random walk actually naturally biased to highly connected users, which in my case will be the influencers. And how it works, so we select a user, and from this user we select randomly one of his friends, and we jump so on to build a chain between the users. So this will be the sample. However, in such an approach, we have the privacy again a problem, because each user in this sample knows the previous and the following user. To compensate this issue, we propose an algorithm to apply anonymous random walk. And simply put, so this algorithm allows the users to decide locally and privately if they would like to contribute to the sample or not. So we will move from a user to another, and each user decide if he will contribute or not, privately. However, one of the limitations of the random walk in general is that you may get stuck in sub-communities, and therefore we propose using multiple random walks, or what's known as random walks with jumps. So to sum it up, we propose to use multiple anonymous random walks in the social networks in order to collect samples. The last user of each walk will receive the sample from the users in that walk. And these users, we call them the prime users. So prime users now they have the samples, and now they will be able to apply privacy-preserving association rules protocols, which is an expensive operation. And by that, we will derive the frequent item sets and later on the rules. To evaluate this approach, we used 3 real-world datasets, as we see here. And as a pre-analysis, actually, we investigated the correlation between the density of users, which means how well the users are connected among each other, and the frequent item sets. So we calculated the density of the users who have common frequent item sets in the Flickr dataset, which we can see it here in the blue dots, and we compare it with the average density of the users in that network. And from this figure, we can learn that all the users who have common frequent item sets among each other, they have higher density comparing with the average density in that same network, which conform actually with the homophily theory. Further, with our experiments, we evaluated, or we focused on the evaluating of the correctness of the frequent item sets based on our sampling. We tried several settings and parameters, and here I will just show a part of the results. So we experiment the sampling with multiple population size. And we can see in the first, in the first graph we can see the recall and the precision curves for different number of populations, and we can see that higher or bigger populations improve actually the quality of the frequent item sets. In the next graph, we compared the different item sets, or the different data sets, and we can see that the 2 data sets from Flickr and LiveJournal, which are more specialized social networks, outperform the output, which is a general purpose social network. And finally, to evaluate the efficiency improvement based on our approach, we evaluated this based on the number of messages we need to perform the association rules or privacy association rules mining. And we can see here the number of messages required in the leading approach or the state-of-the-art approach in blue, where we need more than 80 million messages for 10,000 users, and with 50% sampling rate, we can reduce this to 20 million messages. And finally, improving the privacy came from reducing the data required for the association rules and by applying anonymous sampling. And by that, I would like to finish my presentation, and thank you very much.
Any questions?
Is it working? Yeah. So I enjoyed your slides, and maybe it's an easy question, but I would like to know how the user interact in your system. You said, I don't know, maybe, are you sending a message to all your users and they have to accept or not accept to be involved in the system?
So, for the evaluation, actually, we didn't implement the final. We didn't implement it on actual network. We evaluated based on virtual network. So we have a virtual implementation for the networks, and we generated the frequent item sets in virtual network. So we didn't use it as a let's say final implemented approach. So the users were just part of the implementation, virtual implementation, let's say. So there is no interaction with actual users.
Can I have one quick question? So also you said, I would like to know what happened to those users that are not aware about their privacy.
Not aware of privacy? But
yeah, they are connected, they are online, but they didn't know about privacy or what is happening. They just want to enjoy the social network. And since you are working in a distributed system, and you said by the end you would like to ask the user if you would like to have protection or to get involved, what about those other users?
So our approaches work on the distributed or the decentralized social network, as we said, which usually contain users who care about privacy. However, our goal here actually to improve or to provide the same services even in this social network. So in the decentralized social network or in the hybrid social network, we will have the problem that the data is not centralized anymore, so we cannot apply all the data analytics which usually apply in the centralized social network. So our work actually, our research going in the direction of applying all this data analytics to improve the user's experience in distributed maps. So this would be our goal actually of the whole research.
Another question up here.
Thank you very much. I'm curious about your peer sampling and where this magical 50% come into play.
How 50% sampling rate?
Yes, I mean you introduced 50% random sampling somehow, but how do you come to the conclusion that 50% is actually?
So this is empirical actually experiment. So we did empirical experiment with 50% sampling rate, and we have the results I showed. However, I mean this is maybe I have to highlight that usually when we're doing sampling, we should expect information loss, because usually when we are sampling, we are trying to replicate, as I already mentioned, the whole distribution of the population or specific characteristics in the population. But in the association rules case, actually, what we care about more is the frequent item sets. So if my sample contains the frequent item sets which exist in the population, I may achieve 100% accuracy. So this is Something I would say is more specific to the association rules nature. Yeah.
Perhaps short follow-up, how do you make sure that the same user does not get picked again?
Yeah, so this is part of the algorithm, and I didn't put the details of the algorithm, but every time the users, before he contribute to the sample, he checked if he already did that or not. So there is a check before contributing again to the sample.
Let's thank the speaker again.
Yeah.
Thank you.